The exponential function can also be seen as an equation, where if I just think of the natural one, I have e to the power of, let's say, some number b. And I'm going to get an answer, and the answer, let's call it c. Right? It depends on b and c. B and c are going to be some numbers. Actually, they're all numbers, but I have some flexibility in what they are. We'll stick to the base e. That's not going to change. And if you give me a number b, could be 2, for example, then I'll go and calculate. Oh, I don't know how to do e. I'll go and calculate e to the power of 2 and get an answer. Maybe 5 point something, right? So this is the exponential side of things. The equivalent side, but on the logarithmic way of looking at it, is just a little backwards. The logarithmic side is going to say, you give me the answer of the exponential calculation, and I will then tell you what power of e will get you that answer. So the role of the b and the c are switched around. In the exponential version, the b is the input, and the c is the output that I calculate with this exponential calculation. In the logarithmic version, the c is the input, and the output is the power of e that would get me that c. But the relationship between b and c is the same. It's just looking at it from a different side. So in some basic concept situations, it helps me to think about just casually, informally, what is the exponential function doing in terms of a calculation? It's raising something to the power of something else. Fix the base. Let's take e. You give me a number. I take e to the power of that number, get an answer. Nothing strange. It's more familiar. It's been around in our understanding for a little bit longer. That's the only reason why it's easier. The logarithmic version is saying the same relationship just from the other side. You give me the final answer to your exponential calculation. And the logarithmic function, what it does is it's going to give you the exponent to get you that c. It's just backwards. Given b, calculate c, left side. Given c, calculate b is what the logarithm does. But the relationship is the same. Okay. And sometimes I'm going to come back to this because understanding is always going to be memorization. If I then look at my two properties, which we've listed yesterday, where I can't remember which one I did first, but I'll do this one. I'll do this one first. It doesn't matter which one. Did we write this? Oh, I can't remember if we wrote this property. What did I call this? I'm going to call it C. Did I write it like this? Oh, this doesn't look like something I did yesterday. We might have used different letters, but I'm pretty sure we did this. Let's go. The other one is like this. I'm going to use a B and a C this time. I don't think I did that yesterday. Regardless, it's the same thing. The letters are irrelevant. What does this first one tell me? Now, informally. Well, if I just look at the exponent, that in the box is a number. It's the number that I have to raise e to, the exponent, the power I have to raise e by, I guess is the word, to get an answer of c. I then raise e to that power, and therefore I'll get an answer of c. Sometimes it's easier to informally understand what these functions are doing, and then I don't need to think of it mathematically as a composition always. But that is really what I'm doing. The other version is just the other order of the composition. What is inside the bracket? It's a calculation, an exponential calculation. Given some number b, I raise e to that power, and I'll get an answer. Okay. The logarithm is taking that and outputting the power of e that would get me this thing in the bracket. But because that thing in the bracket is e to the power of b, the power has to be b. Now you can reason through it like this, which I really like as a test of your actual understanding of how these things are related and what they're doing, input output. It's always a good idea. Or you can just memorize this, or you can think of it very mathematically as the composition of two functions, one way and the other way. Either way, they cancel each other, regardless of how you want to think of it. And these properties are very handy. Okay. So these things come up now and then and make my life easier if I can understand what they're doing and they're linked to each other and all kinds of things. There are, okay, so let me think. What's an easy way to do the next bit? Okay, so let's take an example. Actually, before I take an example, I'm all over the place today. I just want to remember something first. So remember, if we talk about derivatives, the derivative of the natural log function, sorry, that looks like a u, it is an n, ln, is 1 over x. And of course, x has to be positive because the log function isn't even defined anywhere else. So now, if we take an example, and we take, for example, the function y equals natural log of, what shall we say here? X squared plus 1 over x minus 1. Let's say something like that. Now it's a little made up, I agree, but it can happen. Now I see, okay, it's clearly a function of a function, right? There is a clear bracket, and there's some stuff inside the log function. Clearly function of a function. No doubt. Now, whether you want to write it out or not is kind of irrelevant. It's whatever level you are at, but let's maybe do that. Let's say u is the obvious inside function, and then my y function is the log of u. I just sometimes say log because it is the main one we use in calculus. So the derivative is going to be the derivative of the outside function with respect to that variable, so it's 1 over u, I'm skipping a step, times the derivative of u, which is not going to be the nicest thing to do. It's going to be a quotient rule, right? Quotient rule, and it's going to look quite unpleasant. Let's do it, why not? So it's 1 over u, so it's going to be 1 over this thing. I could clean that up maybe a little bit by flipping it around. However, that is what it is. Then I have the quotient rule here. Oh, that's going to suck. Quotient rule is the one I prefer to avoid as much as possible. Derivative of the top times the bottom minus the top times the derivative of the bottom. It doesn't look very good, right? It turns out that there are quite interesting and special properties that the logarithmic function follows, and no other function, that allows me to simplify things in a way that's not really intuitive. I have more properties than that, just those two basic ones. But let me make that clear. This is logarithmic properties. Logarithmic function properties. Their home is only here at the logarithmic function. One of them says that if I have the natural log of two things, it doesn't even matter what they are. They could be numbers, they could be functions, whatever. I have an a times a b. I don't even care what they are. Then, interestingly enough, it's the logarithm just of a plus the logarithmic function just of b. That the log of a product is equal to the sum of the individual logarithms. That's weird. That's weird. And that's something that you have to prove. I'll give you a quick overview of how you would prove something like this. You just have to give them names. So let's call this first one, let's call it m, the log of a times b. I don't need the brackets, right? It's one term, but I will. Let's call the next one n, l, m, n. Let's call the other one p. I just need to give these things names. Then, I'm just going to do it quickly. We don't need to know the proofs, of course, but I want to give you an idea of how could this be true? Well, you have to prove it. Well, then what does this first one mean? Now I'm going to use my slightly casual, but correct still, understanding of the link between logarithmic calculation equation and its corresponding exponential version. Because this is a log equation, right? This is an equal sign. There's a log in it. So this would be translated as e to the m equals a times b. Because the answer to a log is the power of e that would get me the thing inside the bracket. Same for the next one. E to the n is going to be a. And same for the last one. E to the p is going to be b. So then if I put it together, a times, sorry, no, not that way. E to the m is equal to a times b. And a itself is e to the n. B itself is e to the p. And when I multiply exponential expressions with the same base, I add them together. And the only way, if I now look at this versus this, the base is the same. It's a basic exponential equation. Therefore, the exponents have to be the same. So m, which was the log of the product, is equal to the sum of the individual logs. And you're done. So all of these properties have to be proven and verified, more so than usual, because they are not intuitive. Why does a log work like this? That I can split a product up? It's not a product rule, it's not a derivative, it's just a log property that allows me to simplify things. Now I can do the exact same thing for division. If I have the log of a quotient, it's simply going to be subtraction. Top minus bottom. So then if I look at the example, and I know we're going a little fast perhaps, there's a lot of stuff, and 4 days is even not enough, but you can always rewatch the video over and over and over. Let me know if you have any questions. If we now look at this function, it was x squared plus 1 over x minus 1 inside my logarithmic function. I can now say, instead of going straight to the chain rule and then having to deal with the quotient rule, I can look to simplify this first by noticing it's the log of a quotient, so it's the difference of the individual logs. I'll stress again, this kind of property is only true for logarithmic functions and only in the way I've listed it. Then the derivative is going to be a difference property first, the derivative of the first term minus the derivative of the second term. Now, sure, I still have the chain rule. This is still the log function of a function, but that inside function is way simpler now. And it might be so simple that I don't need to do the whole u and setup thing. It's the derivative of the outside function with respect to the inside function as a variable, whether I call it u or not, times the derivative of the inside function. Next one, derivative of the outside function, because it is the natural log of something. If I have that something as a variable, then it is this property in the box, which we've seen yesterday. So the second part of the chain rule says times the derivative of the inside something, which is just 1. So this is a much cleaner looking answer, though they are exactly the same. My previous attempt would need some significant simplification to get to this. So by simplifying first, which I should always consider, what is the function in question? Should I maybe try and clean that up first to make my derivative process a little bit easier? And in the case of a log function, the simplification properties are different than other functions. Now, don't see more than there is here. This says what it says and nothing else. If I have inside the log function the product of stuff, I can simplify it and expand it and break it up into something plus something else. If I have inside the log function a quotient, then it's the difference of logs. If I have inside the bracket a plus, there is nothing I can do. It's only a product and a quotient that works. If I have, for example, in this guy over here, the log of x squared plus 1, inside the log, x squared plus 1, there is no simplification property that I can do. It is just the way it is. Don't see extra properties where I have not mentioned them because they don't exist. Okay? Every now and then I see people like that think, well, there's a product property for logs and there's a quotient property, so surely the others as well. No, unfortunately not. I'd love there to be one. It does not exist. Don't make something that doesn't exist. Doesn't work. Okay. But these two, sometimes they're quality of life properties. I like to call them quality of life properties. Because yes, I could have done it without simplifying the log. It's totally fine. If my algebra simplification is up to speed, there's really no problem. I can get around this. But it can also be so much easier to work through a derivative question if I consider the simplification of the log function first. So it's not really a necessity. It really is just a quality of life situation. Okay, so these two properties are very much at the lower end of my priority list. I'll give them a little dot, single dot. The original properties that I listed up here, I'll put a box around the dot. So it's a more important property that I can't get around this, but I don't have, yeah, I actually can't live without this property. It's that important. I'm going to put a little circle around the box. It's probably the most important properties. That is at the heart of the relationship between the exponential function and the log, that they cancel each other. I really can't go without these. But how you remember them is up to you. You can blindly memorize them. You can have an understanding of input-output, which I strongly encourage. But you have some flexibility in how to remember them. There are two more that sit in between these two in terms of priority. I don't want to live without them. I can't go far, but I can memorize my way around them, I suppose, sometimes. And I'm going to do one now and the other one tomorrow, maybe, or later today. Let's give it a dot and a box because it is more important than the product and quotient property, but it's not fundamental to the definition of the function. So it's somewhere in the middle. Now let's just see what it says. If I have the log of, how should I say it in the simplest way? I'll say it like this. If I have something to the power of something else, it doesn't matter what those somethings are. There could be variables in A and in B. There could be just an x to the n or x to the power of something. It doesn't even matter. Doesn't matter. Interestingly enough, this on the left evaluates to the same as this does. It's not intuitive how on earth this could be, and one would have to go and prove it. And I would feel better if we do prove it. But I have this power simplification property that inside the log function, the exponent can quote unquote move to the front of the log. That's so weird. So weird. How would we quickly prove this? Well, in a very similar way. Let's say, let's call n, I guess we use m, right, as the first one. And let's say n is the second log. And our strategy for most of these are to rewrite them to the exponential version, which I'm more comfortable with. So the exponential version, and then I'm using these inverse properties. No, not the inverse properties. Well, in a way, the box, the relationship between the two, says that, okay, if m is the answer to the log calculation, that means e to the power of that answer is going to give me a to the b, the stuff in the bracket. If n is the answer to a log calculation, then e to the n is going to give me a. Okay, so then, oof, that was a then. And again, I'm not expecting you to be able to prove these, but these properties are so strange that they almost feel made up. And it's not a matter of I want properties to work like this, so I make them up. No, they just are what they are. Whether they're intuitive and what I want or not, they just are. Okay, so now what do I have here? Let's see. I have e to the m is equal to a to the b, but a itself is e to the n. So it's e to the n to the b. I literally just said you don't have to know the proofs. So no, not in the test. It's simply because they're so weird, people don't understand how they can exist. And at least seeing the proof once makes me personally feel better that, okay, someone thought this through. I just have to use it now. So e to the n to the b is e to the n times b, or b times n. And again, I have a basic exponential equation, so the two exponents have to match. So m is equal to b times n, and I get my top property. Because m was the first log, n was the other log, and that's just the way it is, whether I want it or not. But this is an extremely handy property. Whew, so handy. How you remember it, I don't care. I'm not remembering the proof to remember the property. I just think of the exponent moving. But again, it says only what it says. So for example, if I have y equal to natural log of let's say x squared plus 1, my favorite, to the power of 10. Remember, this is one term, so it's all inside the log. We don't put more brackets there, though you're welcome to. It just looks a little messy. So please understand what is inside the log and what's not. Very important, of course. We have mentioned that. Now, I have some options here. And again, it's for the most part, you can get away without these properties. Just like we did, but then we ran into the quotient rule in that one, right? You could do the same thing here. You can say, no, I'm going to treat it just the way it is, go straight to the derivative. Well, then, of course, it's a chain rule, right? It's the log of something, so the derivative is 1 over the something times the derivative of the inside something, right? And by now, I don't want to write every chain rule out in detail. It's going to take too long. It's going to look too messy. We ideally want to be able to do a chain rule by just talking through it. So if you're not comfortable with this, practice chain rule more until you can skip the whole U setup. So then this one would require, I'm just going to copy this first part. It's done. That's another chain rule. Function of a function. Inside function now is x squared plus 1. Inside something to the power of 10. So the derivative of something to the power of 10 is 10 times the something to the power of 9. I don't really care what the something is. The second part of the chain rule then looks at the inside something. Derivative is 2x. So it's not that bad. But because this was technically a function of a function of a function, I have a couple of sequential chain rules happening here. It's not anything terrible. Or you could say, I know this log simplification property where I can move the power to the front because this is some inside the log, something to the power of something else. And there is nothing else. Again, don't read more than there is. It has to be an A. The A could be big or small or messy or whatever, but it's one thing to the power of something else. It's something to the power of something else. There's no other things floating around here. Okay. And only then can I simplify it. For example, if I have a 2 there, I can't do that anymore because the 2 is not raised to the power of 10. That's not fitting what I have up here. It doesn't look exactly like this. The property doesn't work exactly like this. I say that because many times people just run with these properties and make up their own variations. No, this is saying one specific thing, nothing more, nothing less. You have to use it correctly or don't use it. So instead, I can go and first say, well, this is perfectly set up. So I need brackets there now, right? Because it's 2 terms. So I can simplify it first. And now my job of finding the derivative is much, much easier. I have a constant times a function, sure. 10 times. I'll emphasize that. Why not? Derivative of the log portion. I know my n looks like a u. I'm just going to let it go. But it's a much easier chain rule situation now. The log of something, derivative is 1 over the something, times derivative of the something, 2x. So neither one was impossible, but it's a quality of life situation for the most part. For the most part. For the properties, for the product and quotient properties, it's a quality of life situation completely. You can always get around it. You don't have to ever use these properties. It's just a matter of how simple do you want your life to be? And by simple, I am, of course, speaking relatively. you can make your life a little easier by knowing those properties. For the, doesn't have a name, the exponent property of the logarithmic function, it's again a quality of life issue. I could have lived without it. It wasn't crucial. But there are unfortunately situations where there's no way around it. It is, I have to use this property. For example, if I have something like, just looking at my ideal example, that equal sign doesn't look good. Equal. Natural log of, let's not make it too bad. Let's go x squared plus 1 again to the power of x. Now this function is really actually a big step up in complexity. There are x's in the base level and in the exponent. But luckily they're inside the log, and I really don't have a choice. I have to do for the exponent property first, because I have no idea how to handle the derivative of something like this. It's just not going to happen. Oopsie. Oh, don't go there. Back. Oopsie. Just want to undo. That's all I want to do. There we go. So in a case like this, I really have no choice. I have to use the log property first. Now, again, I will say, in case you're watching this and you know a lot more, there are other ways, but we don't have those tools yet. So at this stage in our progression, coming across a function like this, we have no choice but to use that property. There are always other ways, but we don't always know them at this stage. Okay. But now this function, oh, totally, I can handle that. What is the first property that I am going to use? Notice that there is an x at the front. So it's not a constant times a function. For the constant times a function property, that guy in front has to be a number. And it is very much, well, it has to be a constant. And it is very much not. So do you want to update your guess? It is not constant times a function because it's not a constant times a function. It's a variable times a function. But you got the times right, leading me to my other option. What could be the other property? Product rule. Thank you. Chain rule's coming, but it's not first. So I'll lay out the product rule for us. It's the derivative of the first times the second plus the first times the derivative of the second. So now I see our derivative of x is 1. I'll write the 1 there to show anyone who cares that I did do it. It just happens to not be complicated. Now for this next derivative at the end here, there is a chain rule, but it's not a terribly hard one. It's the log of something, and the derivative of the log of something with respect to that something is 1 over the something. Notice how I say things. I say things not to sound arrogant. It's not my intention. Everything I'm saying in a specific way, because it may be close to the most efficient way how to think about these things. Then the second part of the chain rule says times the derivative of that inside something. Then I look at the details 2x. And I don't care to simplify it any further, right? So there are some cases for us at this stage where we kind of have to use this property or we can't move forward. We don't have tools to handle a derivative of a function that has x's in the base and exponent level. We don't have that tool. So this property of moving the power in front, please just note when you can use it and when you cannot. Very important. When I can use it, it's usually a quality of life property that I can get around. but sometimes not. Sometimes not. In the case of this bottom function here, there was no x in the exponent, so it's totally fine. I can choose. Do I want to simplify the log, or do I just want to go straight to the chain rule? It's your choice. So I can't really, for some of these, tell you you must memorize this, or you are going to fail. No, most of the time there are options. There are options. That could be good or bad news. So now we are at the end. I just want to map this out again. Let's get a big picture of what we are doing here, what we've done, what have we done, and what is still missing. We started with a general exponential, not equation, function. Call it y, a to the x. We don't know its derivative. So that's a missing piece. Okay, it's okay. We moved on because we got stuck there, and we found the natural exponential function. This wonderful e came to our rescue and gave us the simplest, easiest derivative we could have asked for, where we literally copy the function. It's the one time copying is allowed. Now, then we said, oh, I know inverse functions. So there's another function on the other side of this guy. It is the natural log function. It exists. And we just had to give it a name, ln of x. Use brackets, don't use brackets, that's up to you. For reasons I can't explain just yet, its derivative is 1 over x. We will get the answer to that derivative maybe a month from now. But regardless, it's not that bad, so good. So now I see that there's no direction here, really. It's back and forth. The natural exponential function was a specific one example of the more general family of exponential functions where the base could be many things. So it's really not unreasonable then to think, well, the natural log function refers to base e. If I look at a different base, there should be a log function for all of these exponential functions. There should be a general log function as well. And there is. So let me just link these together. And this is where my chatty understanding, my informal talking through understanding, I think helps me personally, but we can agree to disagree. I have the exponential concept where I'm given an input number b, I calculate e to the power of b, I get an answer. The log function says, give me that answer, and I will return to you the power of e that would get you that answer. It's just flipped around. So now I can say, so this is now the natural case, and I can say the same thing in general. I can say, give me any base. That's valid, of course, so greater than 0, not 1, blah, blah, blah. A is fixed. You give me a b, I raise a to that power, I get an answer. Maybe a is 2. You give me a, let's take an example. Let's take a base 2. You give me a 3, I calculate the answer, I get an 8. No problem. Right, everyone can do that. There is a log sentence on the other side of this exponential sentence saying, you give me the 8, just like I did up here with the c. You give me the 8th, and I want to return the power of 2 that would get me that 8th. That's going to be 3. Now I just need to name this. I'm going to name it log with 2 subscript, and I'm going to say log base 2 of 8. I need to know the base, right? Because for a different base, the answer is not going to be 3. But the relationship between these are the same as they were for the natural case. So in general, I have some base. You give me a b. I calculate a to that power. I get a c. I get an answer. The logarithmic sentence says the base doesn't change. You tell me the answer that you want. I will give you the power of a that gets you that answer. Now, in my opinion, being able to reason and talk through what these things are actually doing and how the numbers in question are linked to each other, so good, so useful, that you understand what these things are and how they work when you can do what I just did. Maybe it won't happen quickly, but I do not want to live without that ability. So if you can get there, you should feel relaxed, because there's nothing then can happen. Nothing can happen. I perfectly understand what these things are trying to say. So then I can update my properties. I'm out of space here. I just now have the same things I had before, but in general. The relationships are the same. Everything is the same. So we're going to come back to this tomorrow, pick up at that point. I just want to highlight that these properties now have general versions as well. So general log properties. I have my first two, that if I have a to the power of log base a of c, it's just going to be c. The only difference here is the base isn't e, but a general a. If I have the log base a of a to the b, you can match it with the versions we wrote for the natural ones. Only the a is changing here. I have my product property, any base, big A times big B is the sum of the logs. Nothing changes. And you can prove them in the same way, you just have to be a little bit more general. You have the log base A of the quotient. I am almost done. Just want to finish here. It is the difference of the individual logs. Then I have the power property, the exponent moving property. Call it whatever you want. I don't know what it doesn't have a name. That would work for any other base as well. All right, so these properties are going to, well, some more than others. The first two and the last one are going to help me a lot when I'm trying to find the derivative of the general exponential function and the general logarithmic function. But of course, that will have to wait for tomorrow, when we will wrap up our discussion. 4-day discussion, not fast. Please note this schedule. Let's see, what is the schedule? Where are we? We are at the end of February. So we've done 3 days of exponential logarithmic functions. Tomorrow is the wrap up. It is a yellow block. Yellow block means the video, I will put the video up very soon. It's there for you to watch in your own time, pause it, rewatch, and let me know if you have any questions. Like I said, the only things we have to do to finish is see how does the derivative of the exponential function change if I don't look at the base e but a general base. How does the derivative of the logarithmic function change if I don't just look at the natural one, but a general base one as well. So not a big thing, but an important one to finish the discussion. So that will not be live. That will be you self-paced video. And then definitely let me know if you have any questions. And then tomorrow, not tomorrow, next week, we are starting Remembrance Day in March. Remembrance Day in March. I'll double check. I'll double check. I can't say for sure. I'll double check. It could have been a copy of it because it was a copy of last semester. I copied last semester and just tried to update it and probably missed one. That'll be our little free day to remember our own work, right? It can be our own Remembrance Day. Why not? Why not? But I'll double check there. Regardless, that's 3 weeks away, so it's not pressing right now. Next week will be the start of part 3, where we focus on graphing and stuff, analyzing functions, that we unfortunately have to start before the midterm 2. The midterm 2 ends with this exponential logarithmic function topic, derivatives. So we start the next part, even though the midterm does not cover that. So next week's material will only be on midterm 3. But I don't want the midterm to be too close in case you need to have some catch up and maybe you're behind schedule, maybe it's difficult, whatever the reason. I don't want the midterm next week. It doesn't give us enough time. So there's this overlap, unfortunately. Tomorrow is the cutoff for the midterm 2 content. It's on the website as well, which topics are covered, but yes. So it's a little bit of an overlap. It's common. It's unfortunate, but all these videos next week will be there for you if you need to catch up. So it's okay. Rather give us enough time for midterm 2 if we need it. And if you're good, well, you're not going to forget it. We're going to do derivatives next week as well. So it's still good practice. There is an overlap in these concepts. So pros and cons. Then we'll have our midterm and then properly continue in third part and so on. Are there any questions about what's coming up? What do we need to do? Remembrance Day aside, maybe it's our math Remembrance Day. Why not? Why can't we remember some math? Take a day. I think we should. It's in the schedule. Can't go against the schedule, right? So March 17th, we're going to remember some math. That's just the way it is. Any other questions? Hopefully there aren't any other holidays that just snuck in. So Easter is a legit holiday for this semester. That's funny. I would not even have noticed that. All right. As always, send me an email. Let me know if you have any questions, and I will try and get back to you as soon as I can. My other course just had their midterm, so I'm flooded with their emails. So if I don't get to your email right away, I apologize. And if you feel that, oh, maybe you missed my email, send it again. It's all good. It's all good. Because it might get lost in the sea of their midterm emails, unfortunately. All right. Until, well, I guess Monday then. If I don't see you Sunday morning for a Q&A session this Sunday morning, I will on Monday again. Until then.